Hello, my name is Alex Balyuk, and today I'm going to introduce you to the concept of secure multiparty communication. In short, it's called MPC, or it's also referred to as SMPC for secure. So let's take a look and understand what it's all about. So let's understand what MPC really is. Multiparty communication is a subfield of cryptography with the goal of creating a method for independent parties to jointly compute a certain function over their input while not sharing the raw data with one another, nor using a trusted third party um, to perform some sort of analysis and return the output. In this particular diagram, four individuals would share their data. Um, the data would get scrambled, then the compute would happen on that scrambled data. That from that data it's not possible to determine its original state, and the calculated output will then be known to all the parties, and they can rest assured that their raw data was never shared. The protocols for secure multi-party communications really enable a set of parties, individual companies, to interact and compute a certain joint function of their private inputs while never revealing the data itself, but sharing the output. The potentials for MPC are very large. It goes to privacy preserving outputs, voting systems, private DNA comparison, private machine learning, and so on. So companies whose data is secret or, for example, HIPAA compliant data, the secure healthcare information, like hospitals and universities can share the patient data for joint computing benefit, but the actual private data will never be shared nor known by the other party, so it could not be stolen or reused. MPC has two very important requirements at its core. First one is privacy, and as I said earlier, data is used for computing, but data is actually never shared. So the goal of the privacy aspect of the requirement is to ensure that nothing should be learned by any party besides the output. So the input will never be known, and the data will be ripped into pieces and sent to different parties. So the only way to only way for the algorithm to fail is if all the parties are really corrupt and share the information with one another. The other aspect is correctness. It's extremely important for the results to be accurate and for algorithms to tolerate corrupt participants, corrupt potentially hacked systems and things like that. And there are different levels of hacking attempts. Um, but the system is smart enough to ban and exclude the jeopardized parties if their outputs are incorrect. And therefore, the correctness of the output is always guaranteed. Let's better understand the security and the corruption tolerance of the MPC algorithm. There can be two different corrupt parties. There can be semi-honest or passive corrupt systems, in which case they're there for nothing but learning what's happening within the systems. They're observing different shares which are being computed on, and they're observing the output, but they are not tampering with the process itself. Now, the other particular case is active or malicious security vulnerability, or not vulnerability, but a hacker, right? Malicious hacker. And that's when the hacker is tampering with the process and modifying its output. So it's deliberately cheating the system, trying to corrupt the data. But as stated earlier, the algorithm is designed in such a way that the output can only be accurate against this shared function. And if it calculates to be incorrect, then all other parties abort, And basically, this way it's possible to identify the corrupt party and exclude it from the computation, to therefore securing the algorithm. And depending on the needs and depending on the requirements in the computation, there are different levels of tolerance for the corrupt parties. For example, when there is a third, let's say n is our number of parties and t is the maximum number of corrupt parties for algorithm to still function properly, a third of all the participants corrupt is still okay for the protocol to be fair and guarantee the output delivery. The other case is when half of the parties is corrupt, in which case the protocol still executes with fairness and guarantees the delivery. And it basically guarantees that honest majority calculation is still accurate. However, in the case of more than half of all the participants being corrupt, there is no way to guarantee the fairness of the computation. In my opinion, the easiest way to understand MPC is through a simple use case. It's basically, let's take a look at the use case where we have three independent parties. We have three friends, Alice, Bob, and Charlie. Alice, Bob, and Charlie all work at the same company, and they want to learn what's their average paycheck. What is their average paycheck without telling one another how much they make, nor without using some trusted party, to some fourth friend whom they can trust, who can keep a secret, and they tell them their paycheck amount, and that person could calculate and give them output. In MPC scenario, they only share the data among themselves in a secret way. We know that Alice makes $2,000, Bob makes $2,700, and Charlie makes $1,500. And by doing a simple math, we know that their average is $2,066. So let's take a look at the next step. This particular slide does not actually use the real mathematical algorithm that's used for share generation. In real life, Shamir's secret algorithm is used. In our case, we're just making up numbers. So the first step would be for Alice, Bob, and Charlie to compute the shares and distribute those shares to one another. So let's take a look at the share generation. In case of Alice, she makes $2,000. 3 shares will be generated because there are 3 parties that will be performing the computing. So Alice's shares will be 5,000 minus 4,000 and 1,000. If we add them up, 6,000 minus 4,000 is $2,000. So we can see that those shares can be mapped back to Alice's paycheck. Same goes with Bob's, 2,700, 3,000 minus 3,000, same 2,700, and same applies for Charlie. Again, in this case, the data is still raw. In Shamir's secret sharing, the data would be cryptographically secure. Let's take a look at the next step. As we saw in the previous step, each individual party generated shares to go to each other party which will be performing the computing. In this case, the data is all coming together. So Alice generated 3 shares and distributed them to every single computing party. So 5,000 was kept for Alice. She gave 1 share of minus 4,000 to Bob, and the other share went to Charlie. Bob did the same thing and Charlie made the same thing. So now we know that Alice has 3 shares to operate on, which are 1 share from Alice, 1 share from Bob, 1 share from Charlie. Bob has done same exact thing and Charlie has done same exact thing. Now, if they perform simple math, they apply the average function. They have 3 inputs, they add them up together, divided by 3, and Alice's average is this. Bob's average is this, and Charlie's average is this. At the end, if they add it up, if we add up these 3 values, which are outputs of each individual compute party, we'll get the same exact average that we got by knowing the values. But if we look back at the shares that each participant received, we can see that there is no way to identify the original value from this. So this is how the algorithm works. It breaks down value into different shares, distribute those shares to all the participants. Those participants apply the same function, same mathematical function, and the outputs of each function are then aggregated in order to obtain the value. Now, it's also worth mentioning that in a real life scenario, even the outputs are not in a raw form. They're in the same share structure where it is it's basically segments. It's not the whole value. It needs to be put back together. Now that we saw a real life example of MPC, and how the shares are created, how shares are distributed to each participant, we're going to look at the real secret sauce behind it, which is Shamir's secret sharing algorithm, which is a cryptographic algorithm used to break down a value into secret shares which are distributed among the participants. And there is also an included secret, and that included secret can only be unlocked if the minimum number of outputs is known. In Shamir's algorithm, it translates into a polynomial function of a degree k minus 1, where k is less or equal to the number of participants, and the strength of k obviously is determined by the requirements of the algorithm. And the only way to discover the secret associated with polynomial function is to obtain the threshold, which is the minimum number of computations from the participating parties. To better demonstrate a real-life example of MPC computation, I've prepared a real-life example using TinySMPC open source library, which is intended for educational purposes and supports basic mathematical operations. And we're going to look at our previous example where with Alice, Bob, and Charlie trying to calculate their average amount of a paycheck while never revealing their paycheck amount to one another. And the program consists of the following components. There will be 3 compute parties involved in taking in the shares and computing the outputs. There will be 3 secret data elements, which is paycheck of Alice, Bob, and Charlie. All the captured outputs will then be calculated, and an average will be displayed. Here is the source code used in the function. We will not spend too much time here, but I just want to highlight that first we have 3 independent parties, and parties are put into this collection for easier distribution later on, where we have a special prime ring size, which is used by Shamir's secret sharing algorithm to calculate numbers. Normally, this value is not specified, and all the shares are computed with an int 64 max value, which are extremely long numbers. But we're using small value to make the numbers easy to read in our use case. Then we have secrets for each of our participants, and they're assigned to, they're linked to a specific source where the computing is happened. Then we will output what the parties know before the processing starts. After that, the shares will be generated and distributed to the known parties. Then we will show the computed shares and what they look like and what the parties know after that event. And then finally, we will perform our output where we'll compute the shared values and display the result. Let's take a look at the output. So here's the output of the process. Just to highlight, we have 3 computing parties, we have 3 data secrets, and then we have distribution of shares among those 3 parties. And a shared output in the next slide. So initially, the parties know nothing but their own secret value. So we can see Alice knows her secret, which is private data. Charlie sees his, and Bob sees his. After that, Alice will calculate, each party actually will calculate their secret shares that will be distributed. So let's take a look at Alice. She has 3 shares. One share is 3048, the other one is 4853, and the other one is 4099. We can clearly see that each share goes to a separate compute participant, and that these values have absolutely no mapping back to $2,000, which is Alice's private data. These values are scrambled and shared, and the only way the final output can be calculated is by combining all the data from all the participants. Here we have our final program output. So we can see that here is a computed shared output from all the other outputs. The computed shares for Alice, the computed shares for Bob, the computed shares for Charlie. Then the values can be decrypted, which adds up to the sum of all of their paychecks. And an average is calculated by dividing the value by 3. And we know that 2066 is indeed the proper value, the correct answer to the problem. Now I want to show you one more thing where I'm going to remove the previous ring size, and I'm going to use the default non-specified value. So the numbers are going to be to the maximum int values. And if you see, I'm going to run the program, clear output, execute the program, and right here you can see what the shares would normally look like. So these numbers are a lot more tricky to decipher and tricky to understand. The computed shares from each individual party is also, as you can see, in a whole different realm of integers. And that's what the real life example looks like. Also, I want to highlight that in this case, this is again simple program running on a local machine. Normally, Alice, Bob, and Charlie would be different organizations, maybe Microsoft and Apple doing some joint customer data calculation, customer data aggregation. Neither of the company wants to share their customer base with one another to not compete for the business, but they can execute such tricky operations with data privacy and security in mind. This research was very interesting, very tricky, and I couldn't have done it without these references. Wikipedia is a great source of information, as well as Winter School of Secure Computation by Professor Lindell. Very useful lectures, really good YouTube channels explaining the processes and mathematics behind it, and TinySMPC GitHub project. Make sure to check it out, and thank you very much for watching. Hopefully this helps you understand what MPC is and how it works and where it can be applied. Thank you.